So this section is going to be about different properties of matrices, more so how we can kind of do operations with them. So first is something we've already touched on. An n by n matrix, so the same number of rows and columns, is a square matrix. And we say it's of order n, because that's the dimension of it. Then we also say that two matrices are equal if they have the same dimensions, so exactly the same number of rows and columns, and their corresponding elements are the same, okay? So this means the one in the first position in that first row, first column is the same for the other matrix as well. And then you go down the list for every other one. So let's try an example of this. We're going to find the values for the variables for which the statement is true, if possible, okay? So again, if I go piece by piece, if I look at the first row, first column, those have exactly the same. Second row, first column, same. 2, 2 position, the same. 3, 3 position, or 3, 1 position. 3, 2 position, the same. What I want to do is I've got these variables w, x, y, and z. So I'm going to go through and I'm going to set those components equal to each other because they should be the same. So if I look at this variable that's in the first row, second column, it better equal what's in the first row, second column. So immediately that tells me my w should equal 5. Okay. If I then move on and I look at my first row, third column, that has x, should be exactly the same as what's over here. So immediately I get x is equal to 6. Moving down, we've got y plus 2 in this spot, should be exactly the same as what's over here. So y plus 2 needs to equal 0, which tells me my y should equal -2. And finally, I've got z to the third, matching that up with its corresponding spot. Z to the third should equal 8. Well, the only way that happens is if z is equal to 2. So these are what those variables should equal to make sure that these elements are the same, okay? So it's very similar to how we were going about solving equations before. It's just we have those components now and we can have multiple equations that we put in there. So when we think about our operations, we have a lot of the same operations like addition, subtraction, and multiplication, but we can't always perform them. So thinking about when we were just adding and subtracting in normal, we can only add or subtract things that are alike. Same thing with multiplication, you only multiply the pieces that are alike. Well, the same idea has to apply here. So to add or subtract matrices, they need to be that same dimension, okay? So they have to have the exact same number of rows and the exact same number of columns. Then all we're gonna do is that operation with the corresponding elements. To multiply a matrix, say just by a number, we can do that with no issue. You're just gonna multiply every single element by that number, right? So let's try some examples of this before we get to the more complicated bit, which is multiplying matrices. And that's where we're going to spend the bulk of our time. So we're going to perform this operation if possible. So if I look at my first matrix, it's got 2 rows and 3 columns. And the second matrix also is the same. So these are the same size, so they can be added. So all I'm going to do is I'm going to get a matrix of exactly the same size. It will be a 2 by 3. And I'm just doing the operations with those similar components. So first row, first column, I just go ahead and add those together. Then I've got first row, second column. So I add those together. And then first row, third column. We add those together. Moving on to the bottom row, second row, first column, we add those. Then we move on to the next two. So we have 1 plus -3. And then finally 3 plus 4 in that last spot. So just adding those together gives me -2 in this first spot, -7 and 7. Then moving down, that gives us 10, -2, and +7. So that is our resulting matrix when we add those together. If I look at the next example, this has 1 row and 2 columns. This is the flip. This is 2 rows, 1 column. So these, although have similar dimensions, they are not the same. So these are different sizes. So these can't be combined. Okay. They have to be exactly the same. And then moving on to the last one, if I want to take -2 and times it by this matrix, I'm just going to multiply every single element by -2. This matrix has 3 rows and 2 columns. So when I go through and multiply them, my result will be the same. But again, I'm still going to have all of these elements, giving myself a little bit of space. I just want to take -2 times every single element. So my resulting matrix will be -14, -6, +6, +2, -8, +10. And so your result is still the same dimension. Okay. And then you can combine these together. You can add multiples of one matrix, subtract multiples of another matrix, any combination of these. The main thing to recognize is when you add or subtract or multiply a matrix by a real number, it is not going to change the dimension at all, okay? The newer operation is going to be when we multiply 2 matrices together. That's going to be a bit more complicated, okay? So the way we know if we can multiply matrices is it's going to be dependent upon the order. So if I have an m by n matrix, if this is my first matrix, the number of columns is the most important thing. The only other type of matrix I can multiply it by is the one that has the same number of rows, okay? So those inner dimensions must match. So essentially, if I'm taking an m by n and I'm going to multiply it by an n by p matrix, these inner dimensions have to match, and the result is going to be m by p, okay? So the order does matter, because if I tried to flip this and do n by p times m by n, these don't match, and we aren't able to multiply those two. So the order matters, and you can't just reverse it. It might not work, okay? So I'm gonna try a few of these to just see if we can do them together. I'm gonna take a long approach for this because it is, again, a brand new operation. But if I start with this first one, a times b, I wanna make sure I can find this, and I want to see what the result of multiplying those matrices is. So my first matrix has 2 rows and 2 columns. And I'm multiplying that by a matrix that has 2 rows and 1 column. Okay. So because these inner are the same, we can go through and multiply. And the result is going to be these outer pieces. So the resulting matrix is a 2 by 1. So you have 2 rows, 1 column. So again, how we denote that is this is the first row, first column, second row, first column. So we're gonna have 2 numbers in the end, okay? So I'm gonna start by finding this top one, A11 of my resulting matrix. So to find A11, we use row 1 of the first matrix. And column 1 of the second. Okay. When I go to do this one, I use the second row from the first matrix and column 1 of the second. So I'm going to go through and I'm going to show you just by highlighting these. Okay. What I want to do is I want to take this first row and I'm going to multiply it by the first column. So we're going to kind of go down and we're going to multiply the corresponding elements. And we're going to add them together. So my resulting A11 is I start with my first thing in each one. That is 1 times -1. Then I add to it, moving right and down. So 2 times 7. Okay. So this gives me -1 plus 14. My result is positive 13. So again, I'm using these two to find the first resulting thing. And we start by going with the first in each spot and then the second in each spot. To find A21, we use row 2 of the first matrix. And column 1 of the second. Okay. So again, I'm going to go ahead and copy this and move it down. But now I'm going to multiply this row with this column. Okay. And so I go in order. First spot in each is 3 and -1. So we multiply those. And then we add, moving down the line, 4 and 7. So that gives us -3 plus 28, which is 25. So if I were to multiply these two matrices together, again, this is a 2 by 2, this is a 2 by 1. The result is a 2 by 1 because these match. The first one gives us 13. And the second gives us 25. Okay. So again, to find the first one, we took this and then multiplied it by each corresponding one. And then we took this and multiplied by each corresponding element. Okay. Let's try a bigger multiplication. So we'll move on to this one next. This matrix is a 2 by 3. This is a 3 by 2. Those match. So the result is the outermost things, which is a 2 by 2 matrix. So I have 4 elements to find. Okay. So we'll start with A11. I'm going to go ahead and just keep duplicating this because I'm going to use it for every single one. I use the first row, the first column. And so we go down the line. I take my first element in each of those pieces and multiply them. Then I add, moving down the line, 2 times 0. And then add, moving down the line again, -1 and 3. So that gives us 1 plus 0 minus 3. And the result is -2. Okay. So my element here will be -2. I'm gonna go ahead and highlight that so I don't lose track of it. Now let's go ahead and let's move on and do the first row, second column. So I'm gonna get my 2 matrices that I'm multiplying in and erase what I've done. Now here again, this tells you what to pick from the first matrix, and it's always row, then column. So here we're using the first row, the second column. So the first row, the second column. Okay. So these each have the same number of elements. So when I go to find this one, we go down the line. We have 1 and -2 in the first spot of each. Then we move into the second spot, which is 2 and 1. And then the third spot, which is -1 and 5. So multiplying those out gives us -2 plus 2 minus 5. So this element is -5. Okay. So I have my top row done in my resulting matrix. Now I want to move on to the bottom row. So now we're going to go ahead and we're going to find a 2, 1. So here we use the second row, the first column. So the order is row, columns. So second row, first column. Okay. So going down our list, we've got 4 times 1. Then we add the next spot, -3 times 0. And then add the last spot, which is 2 and 3. So that gives us 4 plus 0 plus 6, resulting in 10. Okay. One last one to find, and that is going to be our second row, second column. So here we use the second for both. So second row, second column. So we have 4 times -2 in those first spots. Then we've got -3 times 1. And then 2 times 5. So that gives us -8 minus 3 plus 10, which leads us to a -1. Okay. So the result of multiplying these two matrices, squeeze it in here. The result is a 2 by 2 matrix. So when we went through the first one, we did the first row, first column. And so when we multiplied this first row and this first column, that result we found out was -2. Then when we did first row, second column, the result is -5. So first row, second column. Then doing second row, first column gives us 10. And then second row, second column resulted in -1. Okay. So the more you do these, the less you have to go through and do step by step and highlight. But again, while we're getting used to things, I'm definitely going to go through and show you all of those different pieces. Okay. So let's try one more. And if I look at this one, the dimensions of this first matrix are 3 rows, 2 columns. This one has 1 row, 3 columns. So if I'm comparing these, I do not have that same inner number, so we cannot multiply these. Okay. So the order is going to matter for multiplication. So in this current state, we cannot multiply the two. Because the inner dimension does not match. The reason for that is if I sit here and I try to do my first row and my first column, I could multiply these two, but then I have nothing to match up with the 4. So there's not a way to do that equivalent process of these. However, if we did switch the order, that would be this matrix times this one. Okay. This matrix is again a 1 by 3, this is a 3 by 2. Now that inner dimension matches, so we can multiply these. And the result is a 1 by 2 matrix. Okay. So you can go through the process of that, but in general, the order is important, so you cannot just reverse them. It's not like when we have 1 times 2, that's the same thing as 2 times 1. The order doesn't matter. With matrices, the order does because we are storing data, okay? And then just for good measure, I'll go ahead and actually multiply these 2 out just so you can see another example of this. So I think it's beneficial. Let's call this one D. Okay. So again, my result is a 1 by 2. So that means there is 1 row, 2 columns. So the first element's first row, first column, first row, second column. Okay. So starting with A11, 1. I need to use my first row and first column. So going down the line, -2 times 2, plus my middle term is 3 and -4, and then 3 and 1. So that gives me -4 minus 12 plus 3, and that would give us -13. Then I have 1 more to find, which is my first row, second column. So I take this and I times it by the second column. So we've got -2 times 4. Then 3 times 0. And then 3 times 2. So that gives me -8 plus 0 plus 6, resulting in -2. So when we go to multiply these 2 matrices, again, the result, because this is a 1 by 3 and a 3 by 2, the result is a 1 by 2. This first element is -13, and the second element is -2.